Okay guys, let's take a look at today's lesson. What we're going to be doing today is we're going to be looking at systems of polar equations, but this time instead of using a calculator like we did just to introduce it, kind of see what's going on, we are going to be doing those by hand. We're going to investigate two different methods, and each method does something different for us, so we're going to practice both. The first method, method 1, is what is going to find us the true intersections of the polar curve. Now let's talk about what I mean by true intersections. We have textbooks. Okay, so yes, I like reading Precal and calculus textbooks. It's just a thing. So some textbooks, they disagree. Some authors disagree on polar intersections. Some authors would go with this, that the true intersection is where they intersect at the same angle measure. That's a true intersection. And some authors go with, well, if they intersect, they intersect, period. So what we're going to distinguish the two, because I think it's important to at least know that there's a difference. So the method 1, this is going to give us our true intersections. And to be honest, method 1, the procedure for method 1 is much easier than method 2. And maybe it'll bring some love for polar for you. You know, maybe you start loving polar when you're going to see the difference between the two. Method 2 is a bit more intense. So method 1 is going to give us true intersections, just where the actual angle measures would coincide. Method 2, what method 2 is going to do is it's going to find all locations. All. Because when we take our polar equations, and we put them in rectangular form, is there any distinction in rectangular form? I mean, the point is what it is, right? Other than, let's talk about to compare. If we compare rectangular form to parametric form, parametric depended on the time, right? So the lines or curves could cross, and they might not really cross because the time would be different, right? Remember the spider and the fly thing that we did? All right, so same thing with polar. Polar depends on the angle measure. If they cross at the same angle measure, then they actually cross. Well, in rectangular mode, that doesn't matter at all. If they cross, they're going to cross, period. So what this technique does, it's going to pick up all intersections. Not just the, what I say, quote, true intersections, but all of them. And we're going to practice both of them. All right, so let's talk through the procedure. How do we do each one? So to do the true intersections, what we would do, we're going to graph. So you'll have a graph, or you would need to graph. You graph the polar equations, and you look at the graph, and you kind of get an estimate. I mean, how many solutions do you think there are? Kind of figure out how many you think they are. Then we would solve. We're going to solve the polar equations using substitution. Just solve a trig equation, which we should be very comfortable with by now, I'm hoping. It's not ending, right? The never-ending question on quizzes and tests has been, the equations. Then we just make sure, just check our work. That's really all that is saying. We just check our work. On method 2, what we're going to do is we're going to actually go into rectangular form. We're going to take the polar equations and we're going to put them in polar form, in rectangular form. We're going to go from polar to rectangular, and then we're going to solve the rectangular equations. Okay, so that's and then we're going to convert rectangular coordinates to polar coordinates, and then we're done. Okay, so let's practice. What we're going to do on the next slide is we have one example that we're going to do both ways. We're going to do just regular true intersection way, and then we're going to do all intersections. Okay, so let's graph it first. We're going to start with method 1. So method 1 requires us to graph. So this is cosine. We probably don't even need the Cartesian coordinates for this anymore. I bet we're very comfortable with graphing cosine. If you recall, we just really need one period, or just to pi. Half of a Cartesian period to graph cosine. And so this grid, if we don't make any indication, it's in ones. But that would make our graph really small, and I would like to make it larger. So what I'm going to do, and what you can do, you're certainly welcome to, is to put a scale down here. We really wouldn't want to put numbers on every, location, because that would kind of get in the middle of our graph, right? Because these are, well, it would get in the middle, and we just wouldn't really like that. So what I'm going to do is I'm going to say r's are by halves. So my r's here are going to be by halves. They're not going to be by ones, so that I can make the picture bigger. So you can make the scale anything you want when you're graphing. Just tell me what it is. Just write me a little note to tell me what it is. So I'm supposed to start at a 1. So on my scale, this is actually a 1, right? At 0 is 1. Then at pi over 2, I'm at 0. Then at, let's see, pi, I'm at a -1, so that takes me back around here. So that's my first graph. That's cosine. So now let's graph 1 minus cosine. Okay, so the sinusoidal axis has been shifted up 1, and my amplitude is 1, and cosine is upside down. So it starts down and goes up. Okay, so let's graph this one and see what's going on. So this one starts at an angle measure of 0, r0. So it starts here. Then at pi over 2, it's at 1. So for me, my 1 would be right here, right? Because my scale is halves. So this is what we look like. Then at pi, I'm at 2. So, but my scale, because I'm at halves, I would be here at the 4th ring. So we come around. Then at 3 pi over 2, I am back at 1, which by my scale would put me here. And then what do we have? Then at pi, 2 pi, we are back to 0. Okay. So it looks like we have 3 possibilities of intersecting. Right, we've got the pole, and we have these 2 little areas right here. So let's keep going on method 1. So method 1, we graph, then we solve them by using substitution. Since these are both equal to r, why don't we just make them equal to each other? So cosine theta equals 1 minus cosine theta. So I add the cosine over, I get 2. Cosine theta equals 1, or cosine theta is 1/2. So let's think about our unit circle values, where cosine would be 1/2. Let's see, cosine would be 1/2 where it's really tall, right? Because that means the x value would be shorter, so here. So what, at pi over 3 and 5 pi over 3? Okay, those would be our angle measures. So let's look at our graph. Yeah, we look like we got about a pi over 3 and a 5 pi over 3. It looks like these 2 intersections right here. Now just note, we're just sketching. You know, some of you may be like, can do this beautifully. Me, I'm just kind of sketching. And it doesn't have to be exactly at pi over 3. It's kind of hard to make it exactly there, right? I mean, I know a calculator can do it, but we're just sketching. So we have pi over 3 and 5 pi over 3. Now, how do we find the r value? Are we comfortable with finding r values? We just take the angle measures we found and plug them in, right, to get the r value. And it's pretty straightforward, right? If I put a pi over 3 in, I get 1/2. So our r value is 1/2. So our polar solution is 1/2 pi over 3 and 1/2 5 pi over 3. Okay, that's our polar solution. And we go over here and we circle those intersections on the graph. Okay, how are we on method 1? Method 1 is pretty straightforward, I think. We graph it, we solve it by substitution, we write our answers in circle. Kind of like what we did with the calculator yesterday, kind of, but not exactly. Okay, so now let's go into method 2. Method 2 is just a bit more intense because think about what the rectangular forms of those polar curves look like. I mean, we've been going back and forth to polar form, right? They can be a little bit messy in rectangular form. So this, a little bit more intense to do method 2. So let's do method 2. So our first task in method 2 is to turn our polar equations into rectangular. We're going to go to rectangular form. And the first one is r cosine. So to turn this in rectangular form, looks like this is a good candidate for multiplying both sides by r. So let's multiply both sides by r. So that gives me r squared equals r cosine. So we know r squared is x squared plus y squared, and r cosine is x. So that is our Cartesian equation for that. And I'm going to just kind of underline it so we can pick it out. Okay, let's work on the second one. So r equals 1 minus cosine. That also looks like a pretty good candidate for multiplying everything by r. It looks pretty good for that. So let's do that. So I have r squared equals r minus r cosine theta. Okay, I multiplied everything by r. Alright, so let's start converting. So we know r squared is x squared plus y squared equals r minus x. Now we've encountered these before. If you recall, we want to move all the x's and y's to one side, and so we can get r by itself. So we have x squared plus y squared plus x equals r. And then what is a good technique now? We would square both sides, right? Because we know what r squared is. So we get x squared plus y squared plus x squared equals x squared plus y squared. And that is our second equation. Let's kind of highlight that. Okay. Wow. That is a system that we're going to have to solve. So many times when it's this complex, there is a kind of a cool substitution that's many times available. We are accustomed in our substitution just to solve for one variable and sub in for that variable. I mean, that's just kind of what we do. But do we have to do substitution like that? Do we have to solve for one variable and just plug in for one variable? No, we don't. We don't have to solve for just one variable. So we want to look at the two equations and see if they have anything in common that would help us shrink one or the other equation. And if you'll look, this equation says that x squared plus y squared is x. So what I'm going to do is I'm going to substitute this equation into this one by using this relationship. I'm going to change every x squared plus y squared into an x and solve. That works out quite nicely here, because if you will, so I'm just going to hopefully make this a little bit more clear. So here's an x squared plus y squared. Here's an x squared plus y squared. Those are going to turn into x, because I'm taking the x squared plus y squared out and I'm replacing it with an x. Not a traditional substitution that we're accustomed to, but these pop up for us in this scenario and in other kinds of scenarios. So let's do that. So this becomes x plus x squared equals x. I have just substituted this equation into this one and made it simpler. I was like, who would have thought, right? That kind of mess could turn into something more simple. Now you certainly don't have to do it this way. You could solve for one variable and sub into the other, but you could probably imagine what that would look like. And some of them you just kind of have to do that way. There isn't another substitution. Alright, so let's finish this out. So this gives us 2x squared, which would be 4x squared equals x. Okay, I want to caution you right here and say do not divide off an x. What happens if you divide off an x here? You lose a solution. You happen to lose the solution that isn't a true intersection, which is interesting, I think, but you still lose a solution. And we're in rectangular form, so everything is as it is. If it crosses, we're going to find it. So we're going to factor instead, move everything over and factor. So we factor out an x and we're left with 4x minus 1. So x is 0, 4x minus 1 is 0, so x is 1/4. So here's our two solutions, x is 0 and x is 1/4. Now we need to locate the y values of those solutions. Okay, so x is 0 is kind of easy, right? If x is 0 here, so that's 0, what's y going to be? 0. So one solution, so here's our rectangular solutions. One solution is 0, 0. 1/4 is going to be a little bit more challenging, but not too bad. I'm going to take 1/4 and I'm going to sub it in the smaller one, just because. Could you sub it in this gigantic one? Sure, sure you can. I'm going to put it in here. It'd be a little bit faster. So 1/4 squared equals y, plus y squared equals 1/4. So 1/4 squared is 1/16. So I have y squared equals 1/4 minus 1/16, which is, what, 3/16? So it's y squared is 3/16. So y would be plus minus √3/4. Okay, so I have two other solutions. I have 1/4 √3/4 and 1/4 negative √3/4. These are my rectangular solutions. Now what they want us to do is to take those rectangular solutions and put them back in polar form. It really should be an easy matter to do that, and it serves as a double check for our first method. So 0, 0 in rectangular form can just be 0, 0 in polar form. You see how it's not a true intersection, but it is somewhere they cross? Right? They do cross at 0, 0, just not at the same angle measure. But in rectangular coordinates, that doesn't matter. Right? That doesn't matter. If it's going to cross, it's going to cross. So I'm taking these points into polar, and 0, 0 is one of my points. So I'm going to work on 1/4 √3/4. So this is my x and this is my y. So let's see where we can, let's just write it over here. So I have r squared equals 1/4 squared plus √3/4 squared. So r squared is what, 1/16 plus 3/16, which is 4/16, which is what, 1/4. So if r squared is 1/4, what's r going to be? Plus or minus 1/2, right? So r is plus or minus 1/2. Does that coincide with what we found over here? Yeah, those r values are 1/2. Could we have made one of these r values negative? Sure, we could have written it a different way, just picked up a different angle measure. Alright, so now let's do our theta. So tangent theta equals √3/4 over 1/4. So tangent theta equals √3. Let's see, where would tangent be √3? It would be √3 at pi over 3, right? And what? Pi over 3 and 4 pi over 3. Well, I don't have 4 pi over 3 over here as a solution, do I? Could 4 pi over 3 be a solution over here? It could, right? If I was at 4 pi over 3, what would I need to do? Make a negative 1/2. So these really represent the exact same solution, right? So if I make this 1/2 pi over 3, which we know is one of the solutions, what if I made it negative 1/2 4 pi over 3? Aren't these at the same spot? Right? So this is just a duplicate solution. This one is a duplicate. So now we do this tangent theta of this one. So tangent theta equals negative √3. And that's where we pick up. So let's see, where would tangent be negative? It would be negative over here and here, right? So let's see, what would it be? 1, 2, So 2 pi over 3 and 5 pi over 3. And these are going to give us the solution 1/2 5 pi over 3. All right. How are we with our two methods? We okay? Maybe we have a preference for one over the other? I don't know, probably. Do we need to practice both? Yes. Yes, we do.